Hi everybody. So today we'll be learning how to use Iolite 4. Iolite 4 is the program that we use to to reduce data from the laser ICP-MS. You can get Iolite 4 as a trial version on the Iolite 4 website. You just click download trial, you fill out the information here, and you'll be able to get a copy. I think the copy lasts a few days. So just be ready to reduce it when you get it. There may be a way to get a longer version of the trial as a student, but I don't know as much about that. So anyway, let's learn a bit about Iolite. Let's open up Iolite 4 here. We're going to start a new file. So, today we're going to be doing just the bare basics of Iolite. What this tutorial is really for is Iolite for people who not only have never worked with Iolite before, but are in the situation where they have gone on the laser and they've collected data, and now they need to turn that data into numbers, never having touched any of this stuff before. If you continue to use the laser, you should learn more about Iolite and about the laser than will be present in this video. You should check out the videos that Iolite has about Iolite 4, which I'll put a link for that in the video description. And you should go and play around with the settings on Iolite more widely to figure out what it can do for you. So today we're going to do a quick kind of like test Iolite file. I'm not going to be reducing real sample data or anything, you'll see, but it will show you kind of the basics of how to do everything. So the first thing is we need to get data into Iolite. We need to import the data. So we're going to do import folder. I have a file already spooled up and ready to go here. So you just select the folder you want and you click select folder. There we go. So what will happen probably is it won't work. So the reason why it won't work is because I have sabotaged my version of Iolite. And the reason is, so we were here, I clicked on messages here. Whenever things aren't working properly in Iolite, head down to messages to see what went wrong. And what went wrong was that it couldn't load the file because of an invalid timestamp. So you can see the timestamp here, 2024, 10/08, 15, this is the date, and then the time, 15/01/32, and you can see that it doesn't match the date format here. So this is the first issue that most people encounter. So to fix this, we're going to go to Session, Preferences, Import, and then we have an Agilent instrument. We'll go to Agilent timestamp format, and we'll switch this one to years, minutes, yeah. Or months, days. You get the idea. You need to be able to match the timestamp. Another common format is like this, but you'll need to delete the second or the first month or day variable like that. But to import this particular file, we will use this format. Now let's go back and try it again. Here's our data. We need to import dwell times. It's doing this because this is an older file. It's likely you won't get this message. But I know what my dwell times are for this file. Oops. There we go. Okay. So now that we have the dwell times loaded, we can see that we have 25 channels or different masses that we're measuring. We can see the file names. We want to make sure they're all there. Now we can go to time series. So this time series view is what makes Iolite special and easy to use as a program. So in Iolite, initially greeted with this big blank space. Let's learn a little bit about what's going on just in this user interface here. So as we move down the data, as we move along in the data reduction process, we'll go to data, then time series, then DRS, QA/QC, results, export. We'll just kind of move down this list here. So right now we're in the time series. We can click on this gear in the upper left to turn on one of our variables. Let's turn on, I don't know, iron. Now we'll see. Yeah, sure. So what we're greeted with when we double click one of these is we can see the peaks from the laser being on. So this on the x-axis is time, and on the y-axis is intensity and counts per second. So we turned on iron, and while iron is selected here, we can hit log. Now the y-axis is converted to a log scale. We can turn on more elements if we want. So we can turn on, I don't know, nickel, for example. We can turn that on. You can turn the log view on this as well. If you want to manipulate the y-axis, you click on the right 2. So this allows you to move whichever element is selected up and down, or zoom in and out. I zoom in and out with my scroll wheel. You can also zoom in and out using these buttons like this. So if you want to move left and right or in and out, that's my scroll wheel, and I can click and drag left and right. Okay, so if I right click on here, I'll pull up a list. It's useful to turn on show data sample labels, and then you can see all the sample labels across the bottom. Now, the first thing that we're going to do here I'll turn on, it's good to turn on useful elements, but if you turn on too many, then you have too many turned on, and it's hard to kind of visually figure out what's going on. So let's turn on one more. How about zinc? Why not? There we go. Okay. So the first thing that we need to do is we need to create a background group. So what's happening, let's zoom in. So let's remember how the laser works. Here's an individual analysis here. So when we turn on the laser, let's back up. When an analysis begins, the laser is off. We're just collecting background. So that's what's going on. Here's this particular analysis, mass 1,1. And before we turn on the laser, nothing is going on, and then the laser turns on, and whoop, up comes our signal, right? And then the laser is on for a while, zap, 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 and then the laser turns off, whoop. It comes back down, and it goes back down to the background. So this is what you should be seeing in general, something like this in your analyses. So the first thing we're going to do is we're going to make a background group. Oops. Great. Oops. This is a baseline group, like that. So how we set the background, it's good to do this on iron, is you hit Control and you hold it down, and then you click and drag across your baseline like this. You want to try to avoid any big spikes or anything in the background. And we're just going to go across for each analysis and draw a background. Now, when we do this, you can see there's this little square box, right? There's this box. What the box is through the center of the box is the average value that you're selecting. And the width of the box is 2 times the standard error of the variability in that. So or the standard error of the mean. So it's kind of the uncertainty on that mean value. So we can see if we go over and we select part of the peak with our background, it explodes, and all of a sudden, you know, the variability that we're seeing becomes huge. So this is what's happening here. Okay, you can also click and drag on the bottom of the screen here. And we'll select our backgrounds like that. Okay, so then you double click to kind of zoom everything out. And the first thing that we want to do is we want to look at our background, and we can look back at our other elements. And we want to see this dashed line. This dashed line is really important for backgrounds and standards. And what it represents for the background is it's going to be the background that is subtracted out of our signal for each point in our peak, right? Or actually not each point. You'll see what happens, but this dashed line will end up being the background that is subtracted out of our signal. That's the important thing. And what we want to make sure is we want to make sure that this looks like it's doing something that makes sense. This looks okay. Let's see if I can make it do something crazy. No, it looks pretty well behaved. Maybe I'll just select an element that's probably more of a problem. Here, so this is curved, but this still looks okay. I could try deleting one. That might, yeah. So that makes it go crazy. So what can happen, and I did it by doing a mistake, but it can happen organically, is that your background can sometimes do really crazy things. And what you want to make sure is you want to choose a interpolation method that is going to create sensible outcomes. So the Acuma did some crazy stuff. Nearest is very stable, as we can see. Spline 1, this is nice and stable, but splines can sometimes do wacky stuff. I frequently use step average. I find this to be very stable. So let's put this back in here. Okay. Okay. Put a little piece of the peak in there. Okay. So this all looks good for the background. Next, let's do our standards. So for each standard, we have to write down what it is. So mass 1 is a reference. Right here I right-clicked reference material. It's mass 1. There's a whole list, but it's pretty good at automatically doing this. And you click OK. Then we zoom in on our standards. Just highlight them here. You don't want to highlight the entire peak. You want to skip the very beginning, and you want to skip the very end, because frequently those parts of the peak are pretty unstable. So we'll just kind of collect the top parts like that. And we'll do this for, actually in this run I'm doing all standards. This is called Slim. See, this standard in our lab is called Slim often, but its real name actually is FES1. Okay. So we can, sometimes you'll have a peak that looks funny, like it's not nice and flat, and it's kind of up to you what you want to do. For standards, you generally want to include the entire peak, like that. But for samples, having a funny looking peak might actually mean that you're not just analyzing, you know, a sulfide or a clinopyroxene or a magnetite or something that you intended to analyze. It may mean that as you're measuring, you burn through the magnetite and you begin, or whatever you're measuring, and you begin analyzing something else. And this will cause a really funny pattern with some elements, or with all elements, in your signal. And what you need to do is you need to keep this in mind, and you want to select only the parts of the signal that you feel confident represent, you know, the real material that you're trying to analyze. So last we have NIST 610. Now NIST 610 is the standard. But let's keep it as a sample for this, just to and because this is a sample, what we're going to do is we're going to label each one individually. So for your samples, oops, having the total beam is quite nice, because then it's usually the smoothest, nicest, oops, stop that. It's usually the smoothest, nicest signal, and you can really see your peak easily, like that. Okay, let's do this, and then we'll create, this is another sample, like this. I'll highlight this part, that, and last but not least, now, this is actually a little bit of a weird, so here we can say FES1, mass 1, and this is 610, 1, 2, and 3. So this is a little bit of a funny session because it's so short. Generally, you'll have a lot more analyses and you'll have multiple blocks of standards. If you're putting in your samples by hand, like we're doing here, and you're not using an automated way, you'll need to do it this way. You'll have to click for each sample that you're making a little box on the peak of. You'll need to click Add New Selection Group here, if that's the plus. And you'll have to label it with the name of that analysis. It's a pain, but this isn't the quickest or the easiest way to do it. This is the most intuitive way to reduce your data. There are easier ways that maybe I can explain a little bit at the end of the video, but for now I want to stick to intuitive, simple ways where we can get good data without going over, without digging into the program too much, which you should definitely do, later on as you get more advanced with the program. Okay, this is supposed to be super basics. Okay, once we have our background, our peaks for our standards, and each individually labeled peak for our samples, we're ready to click DRS. The one thing that I want to go back and just check out one more time is to make sure that we have, nice, sensible, just like we did for our background, we need to go and check to make sure the dashed line through our standards looks sensible. Often, I end up just using linear fit. Obviously, here it doesn't look like it does anything, but if you have lots of blocks of standards, I'm sure that doing a linear fit will actually cause an improvement or change in the data. So anyway, okay, so play around with these. Make sure your sample selections are located where you want them. And then we're ready to go to DRS. So in DRS, that means data reduction scheme. This is how we're going to produce the numbers. So first we'll click trace elements. We'll select reference materials. So for my samples, all my elements I'm going to tie to mass 1 here. Just keep things simple. I'm going to put everything on sulfur here. And I think NIST 610 has a few ppms. So if you have an issue with one of your standards, let's say you need a new standard or a value isn't available for one of your standards, you go to Data, you go to Reference Materials, you go to, so I'm saying that because it doesn't know, it doesn't know that this is a standard, so of course it doesn't put anything in. But I'll show you what to do just in case. So we go to Glass, you select the standard that you want, like NIST 610. You go to Data, you scroll down. So it actually does have 575 ppm sulfur here. But if it's not here, you can click Add, and you can add the name of the parameter, sulfur, and then you can say whatever it is. Okay, or you can delete it. Okay, and once you have it added there, click Save up in the top right. So once you add whatever new standard value you have. Okay, now if you're using the computers that are here, they should already have a lot of the standard files that you need. And figuring out what standards to use and what values to use is something that maybe you should ask for help on. So that's something that maybe we can escape some technical stuff about, but for the most part. So anyway, what was it? 575? 575. So to input values, you highlight them, you click value, 575, we're done. If you want to change the units, you can do that here. It will automatically update, you can see. It will automatically update to help you out, which is nice. Okay, once we're ready, we hit crunch data. Done. Then we can check against secondary standards to see if we did a good job. So we go to QA, QC, we hit secondary check, run module, we go to settings and select a particular standard we want. I'm going to pick FES1, and we can see how well the standard ran. This looks, if you've done laser ICP-MS before, this is actually going to look a little bad. But if you've done sulfides with laser ICP-MS, this looks perfectly fine. So I ran MAS1 against, I ran FES1 against MAS1, and these are both nanopowdered sulfide standards, and nanopowdered sulfide standards are not great. So this kind of jaggy looking, it's barely within 25% for a lot of samples. Mercury is really crazy. This is all pretty normal, actually. So this is not great. Generally, if we were doing silicate glasses and we're using NIST glasses and USGS glasses, we should be able to get within 5 or 10%. But these standards and these elements are very difficult to measure, so that's why we end up with results that look like this. So anyway, check with your supervisor or with me to see if the secondary standards that your results look okay, and we'll let you know. If you're sending it to me, I'll probably want to see your entire Iolite file. So just send me a link with your whole Iolite file, and then I'll be able to see everything. That will be the most useful. Okay, we can go to results. I don't use results very much. I think it's so that people can kind of play around with their data a little bit. What's going on here? Maybe you have to, okay. So yeah, so you can, I don't use this very much. I guess this is just a way to get some quick plots of the data. But I hardly ever use this because I just export the data and look at it on my own computer using other programs. One nice thing about this is you can go to the data table though. This is probably the most useful thing, and it will give you your data right away. So these are raw intensities here. You can see what it is on the top. It just says gallium-71, and so these are backgrounds that we collected here, and then these are the selections that we put in, and then these are the average counts that it found, and then this is the 2 sigma secondary error here. If we run down, then now it's in counts per second. So this is the background subtracted peak intensity here. And then this is the ratio of your analyte background subtracted intensity divided by the background subtracted intensity of your internal standard. So this is something that's a little bit more technical, but The reason why they report these ratios is because they'll be proportional to concentration. And finally, you have your calculated ppms here. So that's what that's useful for. Now, after we run the data reduction scheme, we can go back if we want, to the time series. Let's turn these off. And you can see counts per second. This is background subtracted intensity, the ratios, and even the ppm. So if you want to see, for example, how a particular section of your selection, whether that part of the selection will have higher or lower ppms, and therefore including or excluding a part of that selection will increase or decrease your your exported final data, it will bring it higher or lower. This is where you can see all of that. So we can see, that NIST 610 has big spikes in the ppm. If we go in and we select, a range like this, and all of a sudden it might look like higher concentration. It's actually just making the uncertainty explode. It's not really helping that much. Anyway, the final thing we want to do is export. So you're not going to have these. You'll want to click Export to File. So in Export, we'll want stats, not time series, right? We'll want the mean averages. We'll want an Excel format. You can also do CSV format. We'll want the samples and reference materials selection groups. For channels, so we can do the raw intensities. We can do ppms. We want ppms, right? That's what we're interested in. So we'll select outputs here. Then we'll select mean, because we're interested in kind of the average that we got. We'll select the standard error, and we'll select the limit of detection. And you'll need to turn on a type of standard error calculation. There are a variety of other options that we want here. I recommend turning on include RM values for RM groups, and then we'll hit export. So test 2. Okay. So then let's open up the file. And there's always these 4 tabs: metadata, the setting, the Iolite settings, papers they want you to cite, and data. So here we can see the different types of data that we got, right? Remember we used mass 1 as a calibrating reference material, so it's no surprise that we'll actually get very good correspondence between our calculated concentration and the reference concentration, right, for this. What we want to pay more, so this is almost something that you can practically delete. What we want to pay more attention to is our standard that we measured that isn't a calibrating standard, that we measured as an unknown. So if we do a good job at reproducing these values, then that's something that's actually, that we can be very happy about. So that's good. Then we have our sample data here like this, right? So here's NIST 610.1, here's NIST 610.2, and so on. And there's your data. So that's all there is to it. Let's see. Okay, so now that we've gotten all the way here, let's go back and look at some small things that make our life a lot easier. How about that? So, what should we do? Let's first start a new session and do it over again. So, new session, same thing. Oh no, I've erased all my work, right? Not really. It's pretty easy to go back to where we were before if we don't do everything by hand. So to not do everything by hand, go to Samples, Auto Selections, highlight everything, Auto Selections, and then you need to know how long your baseline and peaks are. So our baseline for these samples, I think, was 15 seconds. And I think start trim 23 seconds, that seems about right. Interim 10, maybe we need an interim of 15 seconds. And now we can zoom right over and we can see it's all here already. Yeah, looks like I guessed correctly. Oopsie daisy. Okay. There we are. Okay, so we can see that using this auto selections tool, it automatically can plop a little selection window on all your peaks, which is really nice. It does it by just selecting a period in time. So if we go back and we do this auto selections again, but I make a mistake in the time, like 10 seconds, you'll see that it will be off, you know, it will be off the peak because I gave it, it didn't cut enough time off the end. I need to cut about 5 more seconds off the end. So that's a really easy tool, and then you don't have to go through. It does all your baselines for you that way, and it's a really nice, handy tool to get everything done. And then you can go in and look at each one. So that's one easy thing. Another easy thing is that when you are looking at all this data, it can really get cluttered up with all sorts of stuff, you know. If you need to look at lots and lots of different elements, it can get quite hard. So a nice way to do it is to use the heat map selector. And it works. It's a very simple type of tool. Your each element is on kind of this vertical column, and it's just colored according to its intensity. And so you can go down, you can kind of select, oops. You can go in and press Control to select, where you want the peak to be, like this. You can go in and fix these other ones like that, right? So this is another thing. And this way, if you have one element that's being weird, you'll see it, which is a really nice, bonus. If you have another trick, if you have many samples, then it can be really, really annoying to put in each value one by one. And this is where the import is values comes into play. So you need to make a data sheet where you have one column of names and one column of internal standard values, and it will match the names with the internal standard values here. And this is explored on the Iolite website. So that will tell you about it. Yes, and there's so much more. There's so much more inside this program. I mean, there's an Iolite console, a Python console that you can work in here. You can make maps with it. There's all kinds of stuff that you can do in Iolite. So the sky is really the limit. But for now, let's just focus on turning our spots into good data. And that's what we tried to do here today. Let me know if you have any questions, and good luck.